ground in Electrode Conductor GEC routing should follow Article 250 of the National Electrical Code NEC. The first step involves connecting the GEC to the grounding electrode system, for example, a ground rod or water pipe. Secondly, run the GEC to the first disconnecting means, which would be the main breaker panel. This means the GEC should not be connected to the meter can. The reason for this is to avoid a parallel path for current flow, which could potentially overload the grounding system. The meter can should be bonded to the grounding system using a number 4 American wire gauge, or OG, copper conductor. This conductor is separate from the GEC and is intended to provide a low impedance path for fault currents. Some jurisdictions may allow the GEC and meter can bonding conductor to be combined into a single number 4 AWG conductor. However, this is not the preferred method. It is better to use separate conductors for each purpose. In a 200 amp residential service with a meter outside and a main breaker panel inside, the correct way to run the GEC is from the grounding electrode system to the main breaker panel, not to the meter can. The neutral conductor is connected to the grounding busbar in both the meter can and the main breaker panel. Connecting the GEC to the main panel and then back to the meter is incorrect. The correct way to run the GEC is to connect it to the grounding electrode system and then to the first disconnecting means, which is the main breaker panel. It is crucial to adhere to NEC guidelines for proper grounding and bonding to ensure electrical safety and prevent potential hazards. Understanding the function and correct installation of the GEC and related components is essential for any electrician or electrical professional. The path of the GEC should always be direct and as short as possible. Avoid unnecessary bends or loops in the conductor, as these can increase impedance and reduce the effectiveness of the grounding system. When connecting the GEC to the grounding electrode, be sure to use approved connectors and methods. For example, when connecting to a ground rod, use a listed ground clamp. When connecting to a metallic water pipe, use a bonding jumper around any insulated couplings or sections of the pipe. The size of the GEC is determined by the size of the service entrance conductors, as specified in NEC Table 250.66. Make sure to select the correct size GEC to ensure adequate grounding protection. Inspect the grounding electrode system regularly to ensure it is in good condition. Check for corrosion, loose connections, or any other signs of damage. If any issues are found, make the necessary repairs or replacements promptly. It is important to note that local codes and regulations may vary from the NEC. Always consult with the local authority having jurisdiction, or OG, to ensure compliance with all applicable requirements. In addition to the GEC, other grounding and bonding conductors are essential for a safe and effective electrical system. These include equipment grounding conductors, or EGs, which provide a low impedance path for fault currents back to the source. EGC should be installed in all circuits and connected to all metal enclosures and equipment. Bonding jumpers are used to connect metal parts of the electrical system together to ensure they are at the same electrical potential. This helps to prevent shock hazards and reduce the risk of fire. The neutral conductor is also an important part of the grounding system. In a typical residential service, the neutral conductor is grounded at the service entrance. This provides a return path for current flow and helps to stabilize the voltage. It is important to maintain proper separation between the grounding and grounded conductors. Never connect the grounding and grounded conductors together except at the service entrance. Doing so can create a parallel path for current flow and increase the risk of shock. Ground fault circuit interrupters, or GFCIs, are another important safety device that can help to protect against electrical shock. GFCIs monitor the current flowing in a circuit and quickly disconnect the power if a ground fault is detected. GFCIs are required in many locations, such as bathrooms, kitchens, and outdoor areas. Arc fault circuit interrupters, or RFCIs, are designed to protect against fires caused by arcing faults. RFCIs detect the unique characteristics of arcing faults and quickly disconnect the power to prevent a fire from starting. Surge protective devices, or SPDs, are used to protect electronic equipment from voltage surges. SPD divert excess voltage to ground, preventing damage to sensitive electronics. It is recommended to install SPD at the service entrance and at individual circuits to provide comprehensive surge protection. Regular maintenance of the electrical system is essential for ensuring its safety and reliability. This includes inspecting wiring, connections, and devices for any signs of damage or wear. Any problems should be addressed promptly by a qualified electrician. It is also important to keep the electrical panel clean and free of obstructions. Never store flammable materials near the electrical panel. If you are not comfortable working with electricity, it is always best to hire a qualified electrician to perform any electrical work. Electricity can be dangerous, and it is important to take precautions to protect yourself and others. Always turn off the power before working on any electrical circuit. Use insulated tools and wear appropriate personal protective equipment, such as gloves and safety glasses. Double-check all connections to ensure they are tight and secure. Follow all applicable codes and regulations. Never cut corners or take shortcuts when working with electricity. The safety of yourself and others depends on it. When installing a new electrical service, it is important to plan carefully and follow all applicable codes and regulations. Obtain the necessary permits and inspections. Choose the right size service for your needs. Select high-quality materials and equipment. Hire a qualified electrician to perform the installation. By following these guidelines, you can ensure that your electrical service is safe, reliable, and meets your needs for years to come. Furthermore, grounding electrode systems can involve more than just ground rods or water pipes. Other types of grounding electrodes include concrete encased electrodes, or U for grounds, and ground rings. A concrete encased electrode is a length of bare copper conductor encased in concrete near the bottom of a footing or foundation. A ground ring is a bare copper conductor encircling a building or structure and buried directly in the earth. The selection of the appropriate grounding electrode system depends on site conditions and local requirements. In some cases, multiple grounding electrodes may be required to achieve the desired grounding resistance. The NEC specifies the maximum allowable resistance to ground for grounding electrode systems. If the resistance exceeds this value, additional grounding electrodes must be installed. Ground testing is used to measure the resistance to ground of the grounding electrode system. This is typically done using a ground resistance tester. Regular ground testing is recommended to ensure the grounding system is functioning properly. If the ground resistance is too high, it may indicate a problem with the grounding electrodes or connections. Proper grounding and bonding are essential for protecting people and property from electrical hazards. By following the NEC guidelines and best practices, you can ensure that your electrical system is safe, reliable, and meets all applicable requirements. In the context of the original question, the inspector's concern about parallel paths is valid. Connecting the GEC to both the meter can and the main panel creates a potential parallel path for neutral current. This can lead to current flowing on the GEC, which is not its intended purpose. The GEC is primarily intended to provide a path for fault current to return to the source in the event of a ground fault. By routing the GEC directly from the grounding electrode system to the main panel, you ensure that fault current has a direct and low impedance path back to the source. This helps to trip the circuit breaker or fuse quickly, minimizing the risk of electrical shock or fire. The bonding conductor from the meter can to the grounding system serves a different purpose. It provides a low impedance path for fault current to flow from the meter can to the grounding system. This helps to protect the meter can and any equipment connected to it from damage in the event of a fault. It is important to use the correct size bonding conductor for the meter can. The size of the bonding conductor is determined by the size of the service entrance conductors. The NEC provides tables that specify the minimum size bonding conductor required. In addition to the bonding conductor, the meter can should also be properly grounded. This is typically done by connecting the meter can to the grounding electrode system. The method of grounding the meter can will vary depending on the type of service and the local requirements. It is important to consult with the local authority having jurisdiction or ORG to determine the specific grounding requirements for the meter can. By following these guidelines, you can ensure that the meter can is properly bonded and grounded, providing a safe and reliable electrical system.